how exactly do we take simple physical movement and seamlessly turn it into usable electrical voltage for our homes? This mechanism is what powers entire cities. Inside massive hydroelectric plants, giant turbines spin magnets past copper wire to generate our electrical grid's baseline power. It works on a much smaller scale, too. The induction cooktop in a modern kitchen uses the exact same physics to heat a pan without an open flame. This powerful process is called electromagnetic induction. It is the creation of a voltage by moving a magnetic field relative to a conductor. By the end of this module, you will be able to calculate magnetic flux, determine induced voltage, and predict current direction. Step 1 is understanding magnetic flux. This is a measure of the total magnetic field passing through a specific loop area. To measure this accurately, we define an area vector. This is an imaginary line pointing perfectly perpendicular to the flat surface of the loop. Cautionary tone. Pay close attention to this angle, theta. It measures the angle between the magnetic field lines and that perpendicular area vector. It does not measure the angle against the flat plane of the loop itself. We express this relationship mathematically as magnetic flux equals the magnetic field strength, B, measured in teslas, multiplied by the area, A, measured in square meters, multiplied by the cosine of theta. When we multiply 1 Tesla by 1 square meter, we get the standard unit for magnetic flux, the Weber. Flux gives us a concrete number representing how effectively the magnetic field lines pierce the loop's area, taking their relative angle into account. Step 2 requires motion. A steady magnetic field does nothing. Voltage is only induced when the magnetic flux changes over a period of time. This diagram compares a loop before and after a change. On the left, we have a weak field. On the right, the field intensifies. That change in flux over elapsed time, delta phi over delta t, is what drives the system. We calculate the resulting voltage using Faraday's law. The induced electromotive force, or EMF, equals negative N times the change in flux over the change in time. N represents the total number of turns in the wire coil. Because time is in the denominator, a faster change, meaning a smaller delta t, results in a significantly higher induced voltage. You'll notice a negative sign in Faraday's equation. This represents Lenz's law. The core rule here is simple. The induced current will always flow in a direction that opposes the change that created it. To find that direction, we use the right-hand rule. Point your right thumb in the direction of the magnetic field, and your fingers naturally curl in the direction of the current. Let's apply the rule. If an inward-pointing magnetic flux is increasing, the loop fights that increase by inducing an outward field. Your right thumb points out toward you, and your fingers curl counterclockwise. Conversely, if that inward flux decreases, the loop tries to replace the lost field by inducing its own inward field. Thumb points in, fingers curl clockwise. Faraday's law calculates the intensity of the electricity. Lenz's law provides the direction of flow. Let's apply this to a calculation. Step 4, example 1. We need to find the flux for a 2 square meter loop sitting perfectly perpendicular to a 3 Tesla field. Because the loop is perpendicular to the field, its area vector is parallel to the field lines. That makes our angle theta 0 degrees. We multiply 3.0 Tesla by 2.0 square meters times the cosine of 0, giving us a total flux of 6.0 Webers. Example 2 introduces a time factor. We have a 50-turn coil inside a uniform 1.5 Tesla field. In exactly 0.10 seconds, the coil is crushed from an area of 0.25 square meters down to 0. We start by finding our initial flux. 1.5 Teslas times 0.25 square meters equals 0.375 Webers. Since the final area is 0, our change in flux is negative 0.375 Webers. We plug this into Faraday's law to find the magnitude of the voltage. 50 turns multiplied by our change in flux over 0.1 seconds equals 188 volts. Now we determine the direction. The original magnetic flux pointing into the page is decreasing rapidly as the coil shrinks. By Lenz's law, the coil induces a new magnetic field pointing inward to oppose that loss. Using the right-hand rule, we point our thumb into the page. Our fingers curl clockwise, confirming the direction of the induced current. By combining the mathematical result with the directional logic, we have a complete description of the induced event. Step 5 looks at a specific mechanical application called motional EMF. Instead of a shrinking coil, this involves a moving physical object, like a solid rod, creating a continuous change in loop area. Here is a diagram showing the setup. We have a metal rod sliding across two parallel conductive rails. The entire assembly sits inside a uniform magnetic field, B, and the rod moves with a specific velocity, V. For this specific configuration, we can simplify Faraday's law to a direct formula. The induced EMF equals the magnetic field strength times the length of the rod times its velocity. This simplified equation requires one strict condition. The magnetic field, the rod's length, and its velocity must all be perfectly perpendicular to one another. As the rod slides to the right, it continuously expands the physical area of the rectangular loop. That expanding area increases the total magnetic flux, which drives the current through the circuit. Whether a coil is expanding, shrinking, or a rod is sliding along rails, motional EMF is just another way to apply the core rule. Changing the area changes the flux, which induces a voltage. Let's review our 3 major skills. You now know how to calculate magnetic flux, find the magnitude of induced voltage using Faraday's law, and predict the current direction using Lenz's law. Let's do a final check. Question 1. Based on Faraday's law, what makes the induced voltage larger, increasing the number of wire turns or changing the magnetic flux at a faster rate? Question 2. If a magnetic flux pointing into the page starts to rapidly increase, what direction must the loop's induced magnetic field point to oppose it? Question 3. Under what condition would the motional EMF equation equal 0, even if the rod is moving? If you can answer these clearly, you have mastered the basics of induction. If you hesitated on any of them, jump back and review the relevant step. We'll see you in the next module.